Okay, so this is our final class. Really excited. Yeah, this is the first time I teach a class, so before I did that, I have no idea what teaching a class would be. And then right now I can tell you what it feels like, okay? You guys, maybe some of you have attended thesis proposal or thesis defense, some of you are postdoc here. Imagine doing two times per week, okay? That's what it feels like, because there's actually many similarities, right? Well, first it's about 1 hour. Okay, that's stressful. And then second, you're supposed to know much more than your audience. Okay, that's sometimes difficult. And then everybody expects you to be correct. Okay, and then your audience would, just point out every mistake you made on the blackboard. Okay, and but there's something even worse than that, is that on the thesis defense, if someone asks a really good question, and if you're sure nobody else knows the answer, you can simply say, I don't know. And this is a very good question. We'll study that later. But in a class, usually you can't do that, okay? Because you're absolutely sure someone else in the world knows the answer. Okay? So before we start the class, I want to mention a little bit about the final exam. So I'm finishing up on a little bit details on the exam, and then there will be 3 big problems worth 100 points, and then you will not need quantum mechanics for that. And there's 20 points of bonus questions, and that one would be on quantum mechanics. So if you don't know much about quantum mechanics, you can still score very high. And then I think I try to make it easy, so you guys can tell. I'm guessing the average score without the bonus point is somewhere around 50. Okay, and then that's usually an easy test. Okay, and then we will, normalize everyone's score. Okay, and anything above 30 points is actually easy. Okay, you guys can think about it in that way. And there's one exam rules. I think it's actually will work pretty well for you guys. So the exam time is 2 days. Okay, you can pick any of those days during the exam week. You don't have to, let's say, Monday and Tuesday. You can go Monday and Friday. And then during the days in between, you can study the lecture notes, you can study the textbook, but you can't work on the problems. Okay, so if you see a problem show up as, let's say, fourth mixing, and then you don't know how to solve it, okay, it's okay to study fourth mixing, just don't study this particular problem. Okay, so because the purpose of the exam is to, you can think of it as you guys did a homework, okay, a homework of entire semester, like in 2 days. That's how it's supposed to be. Okay, so last time we talked about fourth mixing, and so I didn't think about this before, but I think right now I want to briefly mention it. Right, previously we say that if you input omega 1, omega 2, you're able to generate omega 3 and omega 4, right? This happens in a waveguide, in a fiber, in resonators. And then it occurred to me this morning that actually some of you is able to do this experiment in the lab, right? You guys have fiber, you guys have 2 lasers. But my advice is not to do it, okay? It might damage your laser, because the power you need to make this happen in the fiber is pretty high. And then when you have high, and then once you don't see it, naturally you might think, okay, maybe I need longer fiber, or maybe I need rise my power level. Okay, once you do 2 of those things, you start to see a Brillouin scattering, backward scattering, and that can get a lot of light into your laser. And if you don't have an isolator, your laser can be damaged. Okay, so yeah, if you want to try that, make sure that it's safe, and then discuss with your advisor, and then don't say you learned this from me. Okay. Okay, so the final topic is Raman Brillouin scattering. So some of you might, if you guys do fabrication, then you're pretty much familiar with Raman spectroscopy, right? It's a way to see the see what elements in your device. Especially for metals, if you have silver and gold, their spectrum just show up, pretty easily. Okay, so so why we bring out Raman and Brillouin scattering instead of including them with the foil mixing? So previously in the foil mixing, actually in all the previous nonlinear process, we have input photon, and then we have output photon, okay? And we always have energy conservation of the photon itself. Okay, we always have energy conservation, but this conservation is strictly on the photon itself, right? For foil mixing, if you input 2 photons, and then you can write 1 plus 2 equals 3 plus 4, right? So we call this elastic scattering. Okay, it's like you can, in this process, you can literally think about the photons as particles. They collide, and then the momentum and energy they conserve. Okay. But there's actually, before people discovered this, the history is that people first see elastic scattering, the Raman scattering. It's in 1928, I think, by Raman discovered. Okay. So there's a whole different category that when you have photon input and photon output, actually the energy of the photon itself doesn't conserve. Okay. The photon will give or take some energy from the material. It has energy exchange with the material. So it's a whole different category here. And so let's start with the Raman process. Okay. So, okay, if we input a photon, and then it will become, after it interact with the material, it will give away some energy to the molecule. Okay, it could be vibration, it could be rotation. Okay, normally those are the two main sources for the energy. And then, because you give away some energy, the output photon will have less, and the frequency of the output photon will be lower than the input photon. Okay. You can characterize this energy as h bar omega. It's a way to characterize how much energy you give away. Okay. And if you plot the energy diagram for this process, okay, for a material, you could stay at, let's say, ground state. Okay, ground state. And then there's kind of virtual state you have in your atom. It's not a real state. Okay. And then there's another state that's called intermediate state. The intermediate state is similar to the ground state, but with the vibration of your atom. So with your molecule. So that your molecule actually has a little bit higher energy than your ground state. Okay. So the process of this Raman here is that first your electron inside the molecule is at the ground state. And then it absorb your input photon like this. Okay. And then it emit an output photon. So in total, your molecule gain some energy. Okay. In that way you can think about it, your molecules start to vibrate a little bit. Okay. So now if you have this picture in mind, now you do the experiment. Let's say omega. You input your photon. You input a very strong laser here. And then you would think, well, you will start to see some light coming out from omega 2. Right. The experiment Raman actually see it's not like this. Okay, this is only half the story. He actually also sees some light coming out of here. Okay. And why is that? Because when we draw this picture, okay, we kind of assume that the photon gives energy to the material. But it's possible that the photon can take energy from the material, right? Unless you cool your molecules or atoms to absolutely ground state, then there's no energy to take. Okay? So there's a second picture. So this side, this process, is often referred as Stokes wave. Anything happen on the red side, if you have a frequency shift towards a lower frequency, we call it Stokes wave. And I don't know enough history to explain why. Okay. So the second process here is also Raman, but your atoms start, while your electrons start from the intermediate state, okay? Because you're at room temperature or you're at high temperature, your molecules would have a little bit of vibration itself. It's not always ground state. Especially for the Raman, for most solid materials, this is roughly like terahertz, tens of terahertz, or let's say tens. Okay, and later we will kind of explain a little bit what you will expect if you look at different material, what the Raman you will expect. Okay, so if your molecules start from intermediate energy level, then you can actually intake omega 2. Let's write omega 2 here. Okay, sorry. So let's write omega 1. Right, the same input, go up to a virtual state, Now this virtual state, this virtual state has a little bit higher energy than this virtual state. It's a virtual state, so it really doesn't matter. Okay. And then this one can emit a photon from this virtual state to the ground state. Okay. And this gives you, let's put it omega 3. Okay. So in this schematic, what happened is that you have an input photon. Okay. And then your molecule is already vibrating. And then it goes into a photon with higher energy. And then your molecule is not vibrating. Okay. So this process can happen simultaneously if it's a spontaneous this is usually this picture is for spontaneous process, and then it can happen simultaneously. Really, yes.
Why does it go to the ground state instead of just the vibrational state?
It can also go to vibrational state.
Sure.
Yeah, yeah.
But what? Just randomly?
No, there's this one you have to calculate exactly what this vibration state is, and then there is a transition probability to here, also here. Okay, so because the energy difference is very small, you can think of them as probably equal probability. Okay, yeah. Unless the electron property on this state is very different from this state. Okay. Yeah. So a natural question we want to ask here, okay, is which one is stronger? Stokes wave, or this is called anti-Stokes. Or anti-Stokes wave. Which one is stronger? Anyone make a guess? Stokes. Why is that? The ground state looks tempting, right? Yeah, you can. You guys can actually calculate this. Okay. So we assume. Let's say we assume omega 1, omega 2, they're much larger than omega, the capital omega. Let's make this assumption first. So for this virtual state, this two state doesn't look that much different, right? It's only a slightly energy difference. So we can safely kind of assume that it has an equal probability to go to here and here. Okay. So now what that means is that how many photons going into Stokes or anti-Stokes completely depends on how many molecules you have here, right? So number of photons you get, let's say Stokes versus anti-Stokes, is proportional to the probability of your atom in ground state, or the number of molecules in ground state versus the number of molecules in the intermediate state. Okay, roughly, this is roughly, we have to make some assumptions. And I think probably statistics physics or thermal physics is not a mandatory class for electrical engineering. But this is actually a useful relationship to remember, because it's actually quite useful in semiconductor. Okay. when you have two energy states and then they're in thermal equilibrium, the ratio of them the ratio of them is the energy difference. Let's write it. You can understand it this way. Okay. It's the energy of your state versus I think I'm missing a minus sign here. Let's see. Yep. Yes, okay. The energy of your state versus KT. Okay, KT is the Boltzmann KT. Okay, and okay, it's here. It's if you plug in and then you use the frequency. While the energy difference here is h bar omega, then you get h bar omega KT. Okay. It's the same as semiconductors. If you have a band and you want to know in thermal equilibrium how many electrons are up, okay, given the bandwidth, band gap, you use the same equation here. So let's do a real material. Let's say glass. Okay, for glass, omega is a wide band, but it's roughly 13 terahertz. Okay. And then there's 2 pi. Yeah. And if you look into Wikipedia, if you're just lazy, don't want to calculate it, at room temperature, Planck constant divided by KT is, there's a unit second here. Okay. So this one goes to HKT 2 pi, and it's roughly 2. Okay, this is at room temperature for glass, okay, very common material. So your Stokes wave versus your anti-Stokes wave is roughly this one. And I think it's a number close to 7. Okay. So your Stokes wave will be roughly 7 times higher than your anti-Stokes wave. Okay. And then this ratio will increase if you have a higher Raman frequency. And one number actually it's useful to remember is KT. So at 6 terahertz, this frequency, okay, 1 photon or 1 whatever this is, phonon or something, the energy of it, it's roughly the KT of room temperature. Okay, and this thing is important because if you need to construct, this is typically a terahertz. Okay, if you need to construct a terahertz system, that means roughly a few terahertz at this range, you really need to consider the thermal perturbation from the environment. Okay, roughly you get half and half. or roughly you get a decent amount of your electrons or whatever it is on the excited state. Okay, if you're doing optics, then this number in optics usually this is like 200 terahertz. Okay, so the probability of you getting into excited state is like very, very, very small. Okay, so that's actually why there's quantum experiment you can do at room temperature. Okay, because the system is not affected by your environment. Now let's do some trick. Okay, this is let's erase this. Okay, let's do this. Okay, I'll do it here. Okay, so this is, well, it's not accurate, but this is roughly how you can imagine a molecule inside a glass, right? You have a silicon and then 2 oxygen. And they have some vibration, give you a vibration frequency. Okay. Now, although this is very this bonding, is really very common in our device, but it's not really that common in biological systems, right? You don't have glass in your body. Okay? In your body, it's usually carbon, hydrogen, and then oxygen. Okay, so this one, I'm not sure if I do it correctly, but there's a CH2. So I think in lipid substance like body fat, okay, you have this CH bond. Okay. So now the question is, who has higher frequency? Whose Raman frequency is higher if they oscillate? Why is that? Yes, exactly. Right. So you have, if this is a classical oscillator, then it's roughly k divided by m, right? So if you have higher mass, right, heavier molecules, then your oscillation would be period would be longer. So in Raman experiment, most people would erase here. They use a very awkward way of, presenting their result. Ideally, you would think, well, why not use frequency, right? Well, no. Unfortunately, they use something called centimeter. They use this. I think they call it is it wave number or something? Okay, so it's kind of I don't know who decided this, but right now there's at least 10,000 of paper using this, and then there's nothing you can do about it. Okay, maybe maybe it's because at first people have difficulty of measuring frequency, so they might measure the wavelength first, and then when you measure the wavelength, it's easier to convert it to like 1/, wavelength instead of calculating the real frequency. Okay, so when you look at paper and you see this, don't panic. Okay, 1 centimeter minus 1 roughly equals to 30 gigahertz. Okay. So for our silica, right, the glass, we have 10 terahertz. Let's make it 12. It's easier. Okay. Right. So we have divided by 30. Get rid of this, and then you have 400. Okay, so this will roughly be the wave number you see from a silica. And also there's CH. Also there's another molecules people look a lot is the water. Okay, so those are roughly from roughly 3,000 because they're much lighter. Okay, and nowadays Raman spectroscopy has been commercialized. You can use them in clean room. I think UVA has one. Okay, and but there's Raman spectroscopy is still very active research areas. Okay, and the direction is actually going into very high sensitivity. This is spontaneous one, so it's not very high sensitivity. You need a lot of photon to generate a small signal. So they use either stimulated scattering or coherent scattering, and because we have limited time, we're not going to go over those. Okay, and so right now, I think the best group doing this is a Harvard group led by Xie Xiaoliang. Yeah, he. Yep. I shouldn't comment anything on that. We're on camera. Okay, so his research is wonderful. Okay. It's indeed. Go to his website. It's indeed wonderful. And what they're able to do is that their microscope can look into the skin of a mouse. Okay, and then by changing the wavelength they want to look, they can see in real time how the body fat move, on the skin, and how the water move on the skin. So when they breathe, well, it's not breathe. When the mouse they have a heartbeat, right? In the heartbeat, then you have some oxygen deliver. Okay, actually you can see the change in real time. It's really wonderful, really beautiful. So go to his website. I think it's I think his middle name is Sunny. Yeah, it's a very difficult name to pronounce if you're not Chinese. So he's a distinguished professor in Harvard. I think he has a joint appointment in Beijing University, my undergrad college. And he also has lots of his alum are now professors in a lot of universities. And yep. Okay, now let's move on, and then this part is gone. And then talk about a little bit about stimulated Raman emission. Yes.
Because we use the statistical physics to describe Raman scattering. That's why, because in Raman scattering you have a many-body system, so it's hard to describe it in a quantum picture.
No, actually we're doing it in a quantum picture, right? Because in classical picture you don't have this distinct state, right? Yeah. So I think your question would be why we're using classical electrical field instead of quantum, instead of using photons. Is that?
Yeah.
Yeah, I haven't thought about that. Okay. Yeah.
And also, as you can see, we have many. Actually, the system is open, and we have many interactions with the environment. So, how can we describe all of them in quantum picture?
I think the most difficult part would be this oscillation state here, okay? Because the energy difference is so small, you have to consider all the environment. So my guess is that there's not much quantum going on there. Okay, you would probably see the states will look like this. You have frequency, and then omega, and then you have a line width. A line width determined by how you interact with the nearby molecules, and then, yeah. And if this line width is very wide, that means whatever you generate there, it quickly dissipates. Okay, it quickly move from here to here. For example, in silica, the bandwidth actually looks like this. And this is 13 tera. Okay. So the line width is roughly also that range. So in most materials, this one is, let's say, terahertz, then your energy goes away really quick. Okay, and think about the coupling, right? We saw before it's usually gigahertz or tens of gigahertz coupling strength, and then now you have terahertz dissipation, right? So not much quantum going on there. But there's an exception that's for crystal materials. Okay, they have for crystal materials. They have really strong bindings. Okay, and usually what they have is a very narrow band, Raman. Okay, and then I know for diamond, it's 60 gigahertz. Okay, so probably there's something quantum there. Okay, if you can rank up your coupling between your light and the Raman and have a coupling ratio, coupling speed faster than that, then you can harness some quantum things here before it dissipates. Okay. Okay. Now let's talk briefly about stimulated emission. Okay. So spontaneous emission and stimulated emission, what's the difference? All right. Previously we have started that in the lasers, in the amplifiers, and also in the difference frequency generation. The difference is that, let's say you have a photon input. We always need an input. Okay. And then you generate an output. Okay. Now, if this output photon can induce a second output photon, then we call this a stimulated emission, right? If the speed of how much photon is generated at omega 2 depends on the number of photons of omega 2, then it's a stimulated emission process. Okay. A way to express this is, let's say, the output of your signal at omega 2 right? If you have a waveguide, input, output, and then this is Z. Okay. The increase rate of your Raman photon, people have measured this experimentally depends on the number of photons of your input, of course, and then the number of photons of omega 2 at whatever z you pick. Okay. This is not. You might wonder, well, then this, then you never see Raman effect, right? Because initially it's 0, right? So this is purely from experiment. People add 1 there. Okay. This 1 is for spontaneous emission. Okay. It doesn't depend on this. Okay. So it's a little bit lousy, but people do it anyway. I think part of the reason is all these are discovered pretty early. So there's a way of expressing this very elegantly, and then without thinking about what's really happening. Okay. And if you do want to derive this, right? You want to derive this, you have to go into solving this, the interaction between the light and this state. Okay, there's no way that you don't know what's going on here, and then you get this equation. And the detail can be found in the nonlinear optics books. Okay, and so often, okay, this is something you can measure in an experiment. How to measure that? You have a very high power input. Okay, proportion equals to coupling coefficient multiplied by E1 squared, E2 squared, right? The E2 squared is proportional to intensity, E1 proportional to the photon number, E2 proportional to the photon number, and then we actually drop the spontaneous emission. Okay, it's just a constant number. And this, you'll get a coefficient that include all the dimension conversion, okay, from I photon number to E. So how people discover this? Okay, so what they do is that they first have a very strong input, E1, much larger than whatever E2 you can measure. Okay. And then you measure an output here. You cut your waveguide or your fiber a little bit. You measure another one. Keep going back. So we can measure the output at different z. Right? And you will see it goes like this, exponential increase. Okay? And the exponential increase makes sense, because if E1 is much larger than E2, then you can take this as a constant. Right? Then the entire dE2 dz equals to a constant E2z. Right? And the solution is something at the beginning, and then EKZ. Right? So if you see an exponential increase, you can always go back and then measure and then derive this. And in case you wonder, well, is it E1 squared or E1, something like this, you just change the power and then see whether it change linearly or it change other ways. Okay. So this is the equation you usually would see in a book, and for many reasons we don't like that, right? We want to calculate the electrical field, right? Because all of our other equations are in electrical field. It's not like this. Let's say you have a material, you have Fourier mixing, you have self-phase modulation, and then now you want to add Raman effect. But somehow they're different, right? So you cannot do that. And one typical way to solve this problem is that actually the curve is that you can kind of guess what can happen. Okay? If you put dz here, let's say it's a wave, right? You want to solve the wave equation. And of course, the coefficient will stay. Right? Makes sense, it will stay. Maybe there's another factor here, right? But it's safe to say that this part will stay here. And then now let's think about it, what we can add in the back, right here. You want to match the frequency. Right? Frequency on the left-hand side should be the same as the frequency on the right-hand side. Otherwise, you will have this term mismatched. So naturally, you will guess it's E2. Okay. And then you also have the complex conjugate of this equation. Right. Now this is equation 1, equation 2. If you multiply equation 1 with E2 conjugate plus E2 times equation 2, then what you will see here is that you now construct this term. And this term is simply the chain rule. Okay, it's simply this. And also you will see, well, now you have to add these two together. Okay, there should be actually a factor of 1/2 here. Okay, so this is how you get from something you can measure in the experiment to something you want to calculate. Okay. So this is equation for stimulated emission in the in the waveguide or in any materials. And the reality is that it's far more complicated than this. Okay, just think about the silica. Okay, the silica has a Raman gain roughly look like this. So you have to consider all the frequency components here. Okay, so there's actually a better way to solve it in time domain, and we don't have enough time to cover that. Okay, so if you're interested, just look at the books, and then you'll have some solution. Now let's move on to the final topic of this class. Brillouin scattering. Okay. So first I would describe what Brillouin scattering is. Okay. And then comes the tricky part. What's the difference between Brillouin and Raman scattering? Okay. So Brillouin scattering Let's say you have a lot of molecules. Okay. You have incident light. And then the energy exchange between your light and your material is that you generate, or you give energy or you take energy from phonon. It's a vibration between molecules, not inside the molecule, between molecules. Right? Think about how sound propagate in air, right, or in any materials. Right? It's compression and stretch. Okay, it's an oscillation form. So it's a relative motion. It's really hard to, draw it. So, say it's a relative motion between the molecules. Okay, it's how you propagate the sound. And this is called phonon. Okay. And again, you can guess there are two ways, right? You can take energy from the phonon, you can give energy to the phonon. Okay. So we only focus on give energy to the phonon. Okay. So it would be look like you have incident light, okay, and then it goes into right. Okay. So before, in the Raman process, we're actually jumping between, you're making the molecules to transist from an energy level to another energy level. Okay. So in this process, we don't necessarily need to maintain phase matching condition. We doesn't need to think about the momentum conservation. Just think about the atom. It can absorb a photon, and then there's no momentum in the photon anymore. The momentum is absorbed to the molecule. So that's okay. For that case, we don't need to worry about it. But for this case, it might be a little bit problem. We're generating a phonon. It's something just like a light. It can propagate. It actually carries momentum, right? So you need to think about not just energy conservation, but also momentum conservation. So for the energy conservation, that's simple. Right? Energy conservation, just like Raman effect. Now, what about momentum conservation? Momentum conservation, we say it's a match of k vector. This is momentum. Let's call it phonon, right? Okay. And what is k? Right? K is 2 pi n divided by lambda, right? Or you can write it as your frequency times refraction index divided by, the frequency divided by the speed of light. Okay, it's universal for a wave. And now we might start to see some problem here. Okay. So let's just write this down. Okay. We have h bar all cancelled. So we have omega 1 c n equals to omega 2 c n plus omega speed of sound. Right? It's a phonon. It propagates at the speed of sound. Okay. And if you move this term to this side, let's say the capital omega is small. Okay. We stay in the regime where omega 1 minus omega 2. Sorry. Right, the phonon energy, the phonon frequency is much, much lower than your photon frequency, which absolutely makes sense, right? Then what we start to see is you move this to here, you get omega 1 minus omega 2, Cn. Okay, omega 1 minus omega 2 is just capital omega. Okay, and it needs to equal to this term. Okay. So what it means is that your phonon needs to have a speed that's close to a photon. Okay, and we all know that's not possible. So the problem here is simply by looking at this is the speed of the phonon is too small, so that the momentum of the phonon is too large. Okay, this term is very small, then this entire term becomes large. The momentum of the phonon is much, much larger than the momentum difference of two photons. Okay. So how can we solve this? Okay. Again, I'm not entirely sure about the history, but I guess again this might be discovered by accident. Okay. So if you look at this equation, the thing you can find is that, well, apparently this is much larger than this. There's nothing we can do about it. But also, your frequency is much, much larger. Your photon frequency is much, much larger than your phonon frequency. Okay. If this is not a minus sign, if this is a plus sign, then it's possible these two can match. Let's just think about it. The phonon, let's say in a device, it's gigahertz. Okay. And then your optical frequency is, let's say, 100 terahertz. Okay. In a solid material, not just air. Okay. So there's 10 to the minus 5 difference. And then your speed of light versus the speed of sound is 10 to the 8th. And then the speed of sound in a solid material, let's say in glass, silica, that's roughly 5 times 10 to the, we should do this, VS. The speed of sound in glass is roughly 5,000 meters per second. And then the speed of light is 3 times 10 to the 8th. So again, roughly 10 to the minus 5. So it might be possible if we don't have a plus sign, if we don't have a minus sign, instead we have a plus sign, then this momentum mismatch can be solved. Okay. So how can you do that? Well, the answer is, let's write it down here. The answer is you have a photon input. Okay. And then what they generate is, once again, you have a phonon. But you have a backwards propagating photon. So if you propagate backward, then your momentum change sign, right? So the energy conservation still is omega 1 equals omega 2 plus capital omega. Now the phonon, well, the momentum becomes h bar k1 plus sign going this direction equals to h bar k phonon minus, because it's propagating backwards, right? H bar k2. Okay. If you move around this, you get, again, substitute the k there, omega 1 plus omega 2 Cn equals to omega divided by speed of sound. This is your momentum matching condition. Now this becomes interesting because let's say you have, so first of all, your phonon frequency is much, much lower than your photon frequency. So this part can be approximate to 2 omega 1 C divided A, right? There's only a little bit difference between these two. Okay. So let's say you have input frequency. Let's say at 1550 nanometer. Okay, a lot of the labs in ECE actually have tons of lasers at this wavelength. Okay, and then what you will see is that at a given material that has a specific speed of sound, then there's only one frequency that can match with your input frequency. Okay. So it means the so it means the phonon generated here has a very specific frequency. Okay. Otherwise, it violates the momentum conservation. Okay. So let's calculate what that frequency could be. Let's say in an optical fiber. Okay. In an optical fiber. Here we can have 2 times optical frequency is, we're using angular frequency here, but we can change that into regular frequency because they're on both sides. Okay. It's 1.4 terahertz. Okay. This is the frequency at 1550 nanometer divided by speed of light. Refraction index of the fiber is 1.45, and then times the speed of sound in the silica. You can look it up online. People have measured this. The material science guy have measured this. Okay, it's roughly 5,600 meters per second. Okay, equals your phonon frequency. And if you do this calculation, okay, it turns out to be roughly 10.5 gigahertz. Okay. It's a very, very small frequency difference. Okay. It's small enough that if you send this light and this light together into a photodetector, fast photodetector, you can actually see a 10.5 gigahertz frequency coming out from your photodetector. So this experiment, actually, Andrea's group and Joe Campbell's group are probably in great position to do this. Okay, just send out a light into a long fiber, collect the reflection, have a circulator there to combine the input and output, then you will see this frequency. Okay. And this used to be a terrible, terrible thing for optical fiber telecommunication. You guys can have a try. Okay. What you can do here is you have a laser. For any group that has a laser that can couple into a fiber, you can do this. First, you go through an isolator. Okay, it's a must-have. Otherwise, you have back reflection light going into your laser. Okay, and then you can have an amplifier, but it's not really necessary. Okay, sometimes nowadays the laser can output 50 milliwatt. That's more than enough to see this. Okay. And then you go to Thorlabs or you go to any other vendors, and then you buy, let's say, 10 kilometer of fiber. Okay, very, very long fiber spool. And you measure, have a photodetector. Okay, you can go with very cheap ones, the thermal ones, and then detect the power. Okay. And what you will see is that as you increase the laser frequency, okay, there are more, as you increase the laser power, there will be more and more loss in the fiber. Okay. So of course you will see more power going into here, but if you calculate the power you detect, power received versus power input, this one will drop when you increase your laser power. Okay. It's because a lot of the power are now being back reflected, okay, by the beryllium. So this is actually a huge problem if you try to send a high power laser, through a long distance, and that's almost really not possible. And the way to do it is you send a small signal first, and then you amplify it after you receive the light. Okay. Okay, we have 5 more minutes, so let's show a little bit how you can measure this frequency. Okay. And first thing you would tell is that if your laser frequency, let's say, increase, okay, to let's say 1 micron. 1 micron is again another very popular frequency. Then this the frequency difference, the frequency of the phonon you will generate actually will also increase. Okay, so it's about 15 gigahertz if you input at 1 micron. Okay. So for all those groups that has fast photodetector, what you can do is you have again, for safety, you have isolator. Okay, and then you split your laser. Okay, you split your laser. You can only have, let's say, 10% of, even 1% is good enough. Then you have something called circulator. Okay, circulator means you have this side going to here, and then the reflection side go out from a third port. Okay, circulator. It's like a traffic island. Okay, and then you add a very long fiber spool. Okay. And then you combine these two, send it into a fast photodetector. Now what you have is you have some light at omega 1, okay, some light at omega 2. When you go in the photodetector, what it would do is E1 plus E2, right? The photodetector will do this, right? Detect the intensity of the wave. And then here you will start to collect you start to collect the frequency difference term. Okay. So this experiment here, if you have an electrical spectrum analyzer, you start to see a very sharp 10.5 gigahertz signal. Yes?
What if the material doesn't have the like 10.5 gigahertz in this Phonon spectrum?
Yeah, it's possible. Yeah, you just look up the speed of sound in that material.
So if the material doesn't have this frequency in its Phonon spectrum, does that mean you don't see Bragg scattering in this material?
Yeah, I know what you mean. Yeah, it's possible. Yeah, you're right. Okay. For regular fibers, it's difficult, right? Because for higher frequency means, so let's say we can draw an analogy. We can do an for optical material. How you stop some frequency? There's two ways. One is to build a periodic structure. Let's say a Fabry-Pérot cavity. The light travel back and forth, back and forth. Okay? So its spectrum will look like this. Okay? So if in some way in your fiber you somehow has, let's say, some periodic structure that act on your phonon. Okay, your phonon can see this periodic structure. Then you start to have something like a band gap in semiconductor. Okay, so it's possible that some frequency simply doesn't exist in your structure. Yeah. Okay, so that's all for this semester. Okay, you guys have a nice final exam week and then a nice winter holiday. Okay.